So safe and secure connected and automated mobility, or CAM, is the primary bigger picture end goal here. To get to that goal, millions, if not billions, of testing miles need to be driven. This simply isn't feasible in the physical world alone, but it is with simulation. Even more so when that simulation is comprehensive in capability, flexible and seamless in testing, and cost-effective to the user. In collaboration with Ford, the University of Leeds, CAN Engineering, and CAM Testbed UK, the UK's world-leading CAM test and development ecosystem, we've delivered a project, a proof of concept demonstrator to address these challenges. We're going to be looking at what scenarios you want to test, how to generate those scenarios, then how you want to run those scenarios in simulation, and then moving through to how you want to understand and analyze the results of that simulation, closing the loop of the testing approach that we've taken in the project. The project has also delivered an end-to-end verification and validation pipeline, which ensures confidence in simulation testing. This pipeline is scalable, it's efficient, and it also makes sure that we've got assurance of the safety and the performance of the system under test and also the simulation itself. To understand what's been achieved in the project, let's speak to our expert project partners, starting with our project customer, global car manufacturer, Ford.
So for Ford, it's all about value, optimizing and improving the quality of development as we produce safer, more autonomous and environmentally friendly vehicles such as this new e-Transit. Simulation presents a huge opportunity for Ford, shifting from physical testing towards greater levels of safe, validated and trusted virtual testing. To realise this opportunity, the approach we take to simulation is crucial.
The modular distributed approach we have taken is fundamental to the simulation demonstrator. This enables comprehensive, flexible and seamless testing across a range of different test setups. To demonstrate the benefits of this approach and the world-leading capabilities involved, we have integrated two systems under test into the simulation demonstrator. The first is Ford Automatic Emergency Braking System for Pedestrian, or ABP, and the second extends this system's capability with connectivity known as Electronic Emergency Brake Light, or EBL. For the first stage of testing, we need to decide what scenario we would like to test.
Selecting the right test scenarios is crucial to understanding the capability of the system under test. To do this, we've used a couple of different methods of scenario generation in the project. At the Smart Mobility Living Lab, we've captured real-world driving scenarios and brought them directly into the simulation, training the system under test on representative scenarios that we know have occurred in the real world. There are other methods of scenario generation that have also been demonstrated through the project.
Our verification and validation pipeline uses scenarios generated via a novel database and a knowledge-based methodology. Scenarios in a standardized format act as an important baseline for like-for-like system comparisons, playing a key role in the certification of vehicle systems. The scenarios we have generated have been uploaded onto the Safety Pool Scenario Database, which is the largest public scenario database in the world, through which these can be accessed and loaded into a simulation demonstrator for execution. With the scenarios prepared, it's time to simulate.
For the first use case, we're looking to see how the Ford system at UTAC Millbrook reacts to real pedestrian here at Leeds. To ensure the pedestrian behavior is realistic, we've integrated our world-leading high-cap pedestrian simulator into the simulator demonstrator. Through cloud connectivity, the pedestrian can interact in real time with the rest of the simulation demonstrator at UTAC Millbrook.
Here at UTAC, we're in the simulator room, which is where everything is coming together all in real time. The Leeds pedestrian is interacting through the cloud connectivity with the rest of the simulation demonstrator. Using the distributed simulation approach, we can easily transition this test across a whole variety of different test infrastructures, such as models, software, hardware, driver, and even vehicle in the loop, where we can get a real vehicle on the track integrated into the simulation in real time over our 4G, 5G gateway. By integrating EDR's vehicle to everything, commonly known as V2X systems, into the simulation, we can take it even further, extending the capability through connectivity to enhance the safety of the scenario.
Incorporating our real vehicle-to-everything hardware via a custom network bridge means we can send the real radio messages involved in the electronic emergency brake light function, which extends the automatic emergency braking scenario. And this extension via V2X improves safety because it allows following vehicles to be alerted to a hazard before they can even see it, thus avoiding or at least mitigating a potential collision. And now that the simulation is complete, our next step is to analyse and understand the results.
By passing results through Hariba Mira's Oracle, we can make a holistic assessment through the aggregation of performance and context metrics. This gives us a tangible, score-based assessment of the system under test that can inform the future scenarios to be tested. This is part of the broader verification and validation workflow that has been developed as part of the project.
Any claim that an advanced driver assistance system or an automated driving system is safe to operate must be rooted in robust and validated test capabilities and processes. This includes the validation of the simulation itself. The verification and validation pipeline we have developed addresses this need, ensuring that the simulation capabilities can be trusted. Our verification and validation pipeline also provides a scalable and an efficient way to validate the performance of the system under test. This is done through understanding the boundaries of the system's capabilities and identifying the failure modes.
So at Ford, we're looking to see how virtual tools can transform our development processes, reducing physical testing and unlocking the power of simulation. This project has given a practical demonstration of how that can be done, showcasing how seamless testing across different test infrastructures and remote operation of capabilities offer a clear path to scaling virtual engineering within our organisation.
Right, well the near future opportunity for this work is really to support the very diverse stakeholders in the CAM community who all need to do simulation-based testing of different sorts using very different technologies, and by giving them a portfolio of offerings, we hope we can do that for them.
I think in both regulatory and also consumer-based testing, this sort of simulation route is absolutely critical. We'll never be able to do all the scenarios in real time. We've just got to bring the virtual side into it. This project goes to some way to answering the question, is this a good simulation?
So the individual simulation capabilities that have been showcased in this video are open for business today. But even at this proof of concept stage, we can see the power of collaborative solutions to solve complex customer challenges, but also wider CAM challenges as well. It is precisely this coming together of diverse expertise and capabilities that will drive the future success of CAM Testbed UK and UK CAM more widely, providing safe, seamless and secure testing for a prosperous CAM future.